All right, so what we're going to be talking about here is the evidence we have that actually supports electron configuration, because we know what the configuration is. We can look at the periodic table, we can tell that it's 1s2, 2s2, 2p1. But how do we know it's actually that? Well, we look at something called photoelectron spectroscopy, or PES. So this PES spectrum can show us how much energy it takes to remove the electrons. So photoelectron spectroscopy is where we take a large amount of energy, so usually UV or X-rays, and then we aim it at a substance. Now, if the electrons absorb the minimum amount of energy to be removed, the ionization energy, they can be ejected. So that's called the photoelectric effect. So basically, if we take photons, so we take light particles like UV or X-ray, we take those photons, we aim it at electrons, we can eject it off. So after we eject the electrons off with a certain amount of energy, the electrons will pass a detector that will pick up the presence of those electrons, and then depending on how much energy we put into ejecting those electrons, it can tell us what the ionization energy is at that point. So all of this will support electron configuration. Well, this is what it's going to look like. It's going to look something like this. So you're going to have little peaks, and then you're going to have an x-axis that indicates the energy that you put into the sample to remove electrons, and then these little peaks represent the electrons that you do remove. So you're going to have a y-axis, and then that's going to be the height of the peak. The height of the peak will show you or tell you how many electrons were ejected at that given energy. So for neon, we have a few more peaks, and then we have even more peaks for krypton. Now, you'll notice that you have these little breaks right here. That just indicates that there's a large jump in energy, so in order to make it fit on the paper, that's what they do. Now, on this particular PES, you'll see that it goes from 0 to 80. So all of these go from a lower number to a higher number. Well, you can flip that around depending on who is drawing the diagram or what kind of PES you have, and it can go from higher to lower. The important thing is that you go to the PES spectrum and find the higher point, and you read from that point on. Okay, so when we're analyzing these spectrums, the peaks with the highest amount of energy are going to be closer to the nucleus. So that's basically the very beginning of our electron configuration, where we have the 1s. Those electrons are going to be the closest to the nucleus. So we're going to look at our spectrum. We're going to find our peak with the highest amount of energy. So here would be 1400, and this would be the 1s peak, and then so on and so forth. Now the height of the peak will give you the number of electrons. So whether you have 2 electrons being ejected, 1, 6, onwards. So start with the peak with the highest amount of energy, and then start reading the configuration from that point. Okay, before we go on to actually analyze the spectrum, I just want to note something. Now remember, energy is equal to Planck's constant multiplied by the frequency of that wave. Okay? The energy that you put into the PES is actually going to be larger than the ionization energy, because what will happen is the electron will absorb the energy to get ejected, and then it also starts to move. It gains kinetic energy, and it needs that kinetic energy to move past the detector. So the energy that you see on the PES is actually equal to the ionization energy plus the kinetic energy of that moving electron. So the energy that we put into it is a little bit higher than the actual ionization energy. And we can also rewrite this using this equation too. Now, when we're looking at this information, I honestly don't think you're going to have to do anything with this equation, but I just want you to note that the energy that the PES reads out is actually a little bit higher than the ionization energy itself. All right, so let's look at a spectrum. All right, so we have 4 peaks on the spectrum. We're going to start with the highest peak. So I'm going to start right here. So remember, it can be flipped. It can start from 0 and then go to 1,000. be careful about where you start reading. Read from the highest energy point. So this will be the highest energy point. So well, the electrons that are the closest are going to be the highest energy peak. So it's going to be 1s. Well, when we look at the height of the peak, it's not telling us 1, 2, or so on the y-axis. You're going to look at it relative to another peak. So right here, this peak is it's about 3 times as tall as this one. So this is going to be 1s2. So there's 2 electrons here. Then we go to 2s. So 2s2. This one will be the next peak in. It's 2p6. And then the last peak, well, that should be 3s and then 2. Now the reason, normally when you read these, you can just assume, okay, so it's 1s, there should be 2 electrons there, because I know that one has to be full because I've got more peaks. The more important part is when you read the last peak. So when I'm looking at the last peak, that height can be different than how many electrons actually fit in there. So this peak could be like this, which would be half of this, and then that would indicate it's 3s1. Because if I'm looking at these peaks, well, it's half the size of that. So it should only have 1 electron. So really, when you're reading the height, it only really matters for the last peak. All right, so now that we have the configuration, we know that it's this. Okay, 6, 3s2. All right, well, I can look that up on the periodic table. Well, that's magnesium. Okay, so what they will typically ask you to do with this is they'll ask you to identify the element. They could also ask you other questions. So let's look at this one. Sodium has a total of 4 peaks, and it's PES. And the energies correlate to the following. Explain the existence of 4 separate peaks. Well, you already know if you have a peak, that indicates that there are basically 4 groups of electrons. So when I look at sodium, sodium's configuration is 1s2, 2s2, 2p6, 3s1. Well, that's 4 groups of electrons right there. There's 2 electrons in 1s, 2 in 2s, 6 in 2p, and 1 in 3s. That's why we have 4 peaks. So we're going to suggest the specific electron and subshells that correspond to each peak. Okay, so we know the ones in higher, or the peaks that have the higher energy will be associated with electrons that are closer to the nucleus, because those are harder to remove. So I'm going to start with this one. Well, 104 should be the first energy level. Then the next energy is 6.84. Well, that should be the next one. Then I would have 3s, or 36s, not s, 7. And the last one should be 0.5. All right, so which peak should be the largest? Largest meaning highest. Well, that should be the one with the most electrons. That should be the 3.67 peak. All right, so let's look at another example. Okay, so neon has this configuration. How many unique peaks are expected to be in the spectrum? Well, there should be a peak for every electron group. So there should be 3. Which electrons correspond to the largest energies? Well, the ones closer to the nucleus. So that would be the 1s2 electrons. And then which peak in the spectrum will have the greatest intensity? Intensity is another way to say the greatest height or the largest. So that should be the 3rd peak or the 2p peak, because there are more electrons. Okay, so when we have PES problems, they can ask us a couple different questions. They can ask us to identify the element. They can ask us why one peak is a greater height than another. They can also ask us why one peak has a greater amount of energy. Because remember, if it's closer to the nucleus, it's going to have a greater amount of energy, or it's going to require more energy to remove those electrons. Now, I wanted to show you this one because this one is, first of all, it's not very pretty. All the ones that you've seen so far have been nice and clean. This is a PES, which has a mixture of different elements in it. So, when I'm looking at these, or this particular one right here, it's the same information, it's very ugly. Okay? Now, it tells you ahead of time that it's a mixture. So it tells you that fluorine's at 0.5, oxygen's about 40%, nitrogen's about 2, carbon's about 26, and so on. Well, it's asking why the 1s peaks are different heights and different energy. Well, remember, the height corresponds to how many electrons we pulled from that group. Well, normally we only pull off 2 electrons. However, we have a mixture here of different elements. So if I'm looking at oxygen, oxygen has the highest percentage in this mixture. So we're pulling off more of oxygen's 1s electrons than any of the other elements. That's why they're different heights. Now, why are there different energies? Well, when I'm looking at this, I have fluorine, and then I have oxygen, I have nitrogen, and then I have carbon. Well, fluorine has 9 electrons, oxygen has 8, nitrogen 7, and carbon is 6. Well, that's the atomic number, right? So fluorine's 1s electrons are going to fill the pool of the nucleus at a much greater amount because we've got 9 protons where oxygen only has 7. So that's why the energy is higher for fluorine versus oxygen and so on.